On section 6.2, which is exponential growth and decay. Personally don't see why you get out of classes to go to a concert, but that's not my decision today.
Definitely.
Yeah. So we have 6.2, which is exponential growth and decay. We are looking at changes in y that are proportional to y. If something is proportional to itself, it's going to be something called an exponential growth and decay model. My daughter that's a pharmacist said this was one of the most useful things because when you get to trying to figure out titrations of drugs and how long things stay in your system, and as far as your body processing and metabolizing and all that, it has to do with this exponential growth and decay stuff in logistics, which is what 6.2 and 6.3 is all about. So if you're going into some type of a medical thing, then there might be some applications here that might not be in some of the other areas. So anytime something says that there's a change in a variable that's proportional to itself, as soon as you see that word proportional, you know there's going to be a k involved. And if it were in the case of your body metabolizing drugs, every drug's going to have a different k because everything gets metabolized differently, which is why they need to know your height and your weight and all of that because that affects your metabolism as well as your chemistry and all that, so, and the drug itself. So there will be a different proportionality constant for everything that you have, and that has to be calculated, obviously. I'm not sure how you do that, but so anytime you see that the change, and a change is a derivative, right? That the change in something is proportional to itself, you know that you're going to start out with dy dt equaling ky. So the change in this object with respect to time is proportional to that object. Does everybody understand what this thing here is saying then? Okay. So if y is a differentiable function of t such that y is greater than 0 and y prime, which is this dy dt, is equal to ky for a constant, you're going to get this formula. So let's see how that comes into play. So we're starting out with dy dt equals ky. Now what we do when we solve this thing to get the original equation is to separate our variables out, right? We need all the y's on one side, all the numbers and x's on the other side. In this case it'll be t's. So if we separate it out, we're going to have dy over y equals k times dt. When we take the integral of each side, we'll have the ln of the absolute value of y equaling kt plus c. Okay so far? Now, we want to get rid of the ln. We want to solve this thing for y. And we've done some of these already, so this is not going to be brand new. We are going to exponentiate each side, which means we'll have e to the ln of y, which is y, equaling e to the kt, excuse me, plus c, which is the same as times e to the c, correct? Because if you have a base times a base, you're going to be adding the exponents. So we're kind of working backwards that way. So if the exponents are added, that means we multiply by common bases. And e is a number, c is a number. If I have a number raised to a number, I'm going to get a number. So remember, I always say a c is a c is a c. So this is a constant c. So y equals c e to the kt. So that's how we get from this proportionality statement to our equation in terms of y. Questions on that? So when you see an equation that looks like this, y equals c e to the kt, you need to know that c is the initial value of y, k is the constant proportionality. If k is greater than 0, it's exponential growth. If k is negative, it'll be exponential decay. Another place you're going to see this formula is in business. Remember that PERT formula that you learned back in Algebra 2? A is equal P e to the RT? Same formula. So if you know an interest rate, whether you're paying it or getting it, okay, that is a continuously compounded interest. It also is the same exact formula. So there are business applications for this as well as medical applications. Okay, let's take some examples. Let's say that the rate of change of y is proportional to y. And we know that when t is equal to 0, y is equal to 2. And we know that when t is equal to 2, y is equal to 4. We want to know what is y when t is 3. Am I all on the screen there? Trying to make it big enough, but not run off the edges. So we know that the rate of change of y is proportional to y. If we know that, where is our starting point?
dy dt equals ky.
That's right, dy dt is equal to ky. So we know that. That's what we start with. Everybody have that down? I see a lot of writing right now. Now, what we need to do is get our initial conditions. And we know that at 0, we have 2. We also know that this equation is going to lead to our y equals c e to the rt, correct? Okay, based on what we did a minute ago. So if we have the point 0, 2, can we calculate c? And can we calculate r? Or k, whichever the case may be. So we want to find those. So if we have 2 unknowns, we are going to need 2 equations, correct? That's why you're given 2 pieces of the puzzle. So we know that y, which is 2, is equal to c e to the kt, which would be 0t. E to the 0t is 1, so we know that c equals 2. So we now have the equation y equals 2 e to the kt. So using our 0, 2, we can find out what c is. Then we were also given the point that when t is 2, y is 4. So if we know that we have y equals 2 e to the kt, we now have 4 equals 2 e to the 2k, and we can solve for k. Divide each side by 2. 2 is equal e to the 2k. How are we going to find out what k is? Use logs. Anytime your variable is in the exponent position, use logs. So the ln of 2 will equal the ln of e to the 2k, which means that ln of 2 is equal to 2k, or k is 1/2 ln 2. That is approximately 0.3466. Whenever you get a k value, keep at least 4, maybe even 5 points, 5 decimals. Because remember, exponential changes very quickly, and your final answer has to be accurate to 3 decimals. In fact, it would probably behoove you to keep the whole 1/2 ln 2 until the bitter end. Okay? Therefore, our model is now y is equal to 2 e to the 1/2 ln of 2t. The question asked us, what happens when t is 3? So we can now calculate that. We're going to have 2 e to the 1/2 ln of 3 times 2, which is 6, and that is approximately 5.657. So we can find that at any point in time. Questions on that? Now, you picked up several pieces of paper, and I think some of the next examples are on there.
Why would that be ln of 6? Because aren't you multiplying like the outside?
Let's see here, what do we have? 1/2 ln 2, oh, you're right. So that wouldn't be, it would be ln of 2 times 3. Yeah, I just plugged in a calculator, sorry about that. Okay there? Good catch. Okay, you picked up a worksheet that was green, I believe. And the next example that I'm going to use is the radioactive example, so let's find that one. Radioactive decay is measured in terms of half-life. Suppose that 10 grams of plutonium, isotope Pu-239, was released in the Chernobyl nuclear accident. Plutonium has a half-life of 24,360 years. That stuff is around for a very long time. How long will it take for the 10 grams to decay to 1 gram? Okay. Since the rate of decay is proportional to y, it's proportional to itself, we know that we have the dy dx or dy dt is equal to ky, which leads us to the y equals c e to the rt. So we know it's proportional. So therefore, we can use this information. What can we glean out of this? What is this information telling you?
X and Y.
X and Y's, okay, so what do we have?
24,360
True. And so what is happening when t equals 0?
Nothing.
When t is 0, how much stuff do we have? 10. Okay, now you said something about the 2,436, or 360 rather. That's a t, right?
Yeah.
Okay. So when t is that number, what's the y?
5.
Right, because it's a half-life. So if it takes 10 grams is what we're looking for, and we are looking for a half-life when it's 5, when y is 5, we want to know what is the half amount going to be. So we have our equation. We know that 10 is going to equal ce to the 0 times t, or 0 times r, which means c is equal to 10. So we now know that y is equal to 10 e to the rt. So that's our beginning amount. We also have this 5 thing, so we know that 5 is equal to 10 e to the 24,360 times r, or k. The rate is sometimes used r, sometimes used k. Divide by 10, we have 1/2 is equal to e to the 24,360 r, or k. I'm going to use k's because I like k's better. What do we need to do? ln. So the ln of a half is going to equal 24,360k. K would be the ln of a half divided by the 24,360. Or k is approximately negative 0.000028454. Or we can keep it as that decimal. We have an equation then of y is equal to 10 e to the ln of 1/2 over 24,360 t. I'm going to keep the exact, because these things change very quickly. We now want to know when will there be 1 gram left. How long does it take to get it down to 1 gram? So it would be 10 times e to the ln of 1/2 over 24,360. That quantity times t is what we're looking for, so we're going to make the y be the 1. And if we use our ln's and we solve that, what we end up with is t is approximately 80,922 years. And it's still there. Nasty stuff. Now, one thing to remember, I would drag this on an AP test especially, and on my test too, I would keep this as an ln and not change it into a decimal. I had a problem, and I'm not sure if I'm still using it here or not, but where if you used 6 decimal places versus 7 decimal places, it made a difference of 80,000. Therefore, since you have to have something accurate to the nearest 3 decimal places, it would probably be a good idea just to drag that thing with you everywhere you went until the very, very end. Okay? Because exponential changes very quickly, and then you don't have to worry about your accuracy. Okay. Next example we are going to use has to do with Newton's law of cooling. Newton's law of cooling is one of those things that you see on a lot of different tests. It states that the rate of change in the temperature of an object is proportional to the difference between the object's temperature and the temperature of the surrounding medium. You bake a cake, you take it out of the oven, you sit it on the counter. Is it going to cool faster on the counter or in the freezer? What do you think? In the freezer, because the temperature differential is different, right? So it's going to cool faster depending on its surrounding area. And that's Newton's law of cooling, has to do with that. Now, have you done that in physics yet, Newton's law of cooling?
They won't be covering that this
They're not going to be covering that this year, because usually that's something that people would have covered. So since you're doing a different class now, maybe you aren't going to see that this year. Okay, so we're going to let y represent the temperature of an object in a room whose temperature is kept at a constant 60 degrees. If the object cools from 100 to 90 degrees in 10 minutes, how much longer will it take its temperature to decrease to 80 degrees? Now this is slightly different because of the surrounding area idea. So from Newton's law of cooling, the rate of change of y is proportional to the difference between y and 60. So that tells me that my dy dt is constant, but it has to do with the difference between your temperature of your object and the surrounding area, which in this case is 60. So it's not just kT, okay? So Newton's law of cooling has a little bit of a twist to it. All right. So what we're going to do then is have to separate our variables. We can't jump right to that CE to the KT formula. So we're going to have to separate. So we're going to take dy over the y minus 60 equals k times dt. Then we'll integrate each side. So we'll have the ln of the absolute value of y minus 60 is equal to kt plus c. Since y is going to be greater than 0, we don't really need to worry about the absolute values from this point on, right? Because it's always, if the surrounding temperature is 60, it can't go below 60, can it? It's not going to cool below the temperature of the area that's around it. So this is going to be at least be 60 minus 60. So we don't have to worry about the absolute value anymore. So we don't have to be concerned about that. Okay, so we now have to exponentiate both sides. So what we're going to end up with is y minus 60 equals our CE to the KT. Or y equals 60 plus CE to the KT. Any questions about how this formula became slightly different? So you have to basically, it's like an initial value question. Where did it start? Started at 60 plus whatever the change in the temperature is going to be. Now, what information can we get out of our statements? Do we know anything about the initial T?
Y is 100 degrees when T is equal to 0.
That's right. So T equals 0, Y equals 100, right? We took it out at 100 degrees. So 100 will equal 60 plus CE to the KT. We're going to put a 0 in for T. So that's going to make this be a 1. So 40 is going to equal C. So we now know that Y is equal to 60 plus 40 e to the KT. Okay so far? What else do we know? Have any other temperatures and times? That's right, after 10 minutes it cooled down to 90. So 90 will equal 60 plus 40 e to the 10k, or 30 equals 40 e to the 10k, or 3/4 is equal e to the 10k, and we want to solve this for k. So the ln of 3/4 would equal 10k, and k would be 1/10 ln of 3/4. We now have an equation, y is equal to 60 plus 40 e to the 1/10 ln of 3/4 times t. So we can now find other temperatures. We want to know how much longer it's going to take to decrease to 80 degrees. Where do we put that 80? In for y. So 80 will equal 60 plus 40 e to the 1/10 ln of 3/4 times t, or 20 is equal to 40 e to the 1/10 ln 3/4 times t. Dividing by 40, a half will equal e to the 1/10 ln of 3/4. I know it's a pain to keep writing that, but it does make a difference. Take the ln of each side and solve for t. We get t is approximately 24.094 minutes. Is that our answer? No.
Please subtract out 10.
Subtract out the 10. Very good. It's, a lot of times people forget that. Because it says, how much longer? Well, 10 minutes is already passed, right? So it's going to take another 14.094 minutes to cool down to 80 degrees. This is a Mongo-sized problem. There's nothing terribly difficult in it. It's just knowing what to do next and the next and next, just to follow through. So that's how Newton's law of cooling works. Any questions on that one? Did you get it all on that one page? I got it on there once, but I had it write really, 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 really tiny. Okay. Next, let's see what's on the other side of this. Suppose an experimental population of fruit flies increases according to the law of exponential growth. There were 100 flies after the second day of the experiment and 300 flies at, now I don't know how you count those things, but anyway. After the fourth day, approximately how many flies were in the original population? So we don't know where we started. But we do know that they are following the laws of exponential growth, so we do know that y is going to be equal to c e to the kt. The other thing to remember is that t is in days, right? These things multiply very quickly, which is why a lot of experiments apparently are done with fruit flies. You get a lot of quick data. Okay. So what do we know?
When t is 2, y is 100.
Yeah, when t is 2, y is 100, so we know that 100 is going to equal c e to the 2k. What else do we know?
T is 4, y is 300.
Okay, so we also know 300 is equal to c e to the 4k. So we essentially have two equations, two unknowns. We're going to need to solve this for a variable. So what I would do is take this top equation and solve it for c. So we have 100 over e to the 2k equals c, and substitute that into the other equation. So then we'll have 300 is equal to 100 over e to the 2k times e to the 4k. Divide each side by 100. 3 will equal, and if we have e to the 4k over e to the 2k, that's going to be what? E to the 2k. If you notice, there's not a lot of calculus in this. There is a lot of pre-calc in Algebra 2 solving exponential equations. The only calculus that's in here is how did we get to the y equals c to the e to the kt formula. That's the calculus piece. The rest of this is just kind of algebra-like. Okay, we need to solve this, so the ln of 3 is equal to 2k, and k would be 1/2 ln of 3. We're going to substitute that back up here where our c was. So c is going to be 100 over e to the 2k, which would be ln of 3. And if you multiply this out, it is approximately 33. So that means that we started with 33 fruit flies, and so we started with 33 flies. And our equation would be y is equal to 33 e to the kt. We weren't asked for anything else, we just needed to know the original amount. So we could continue if we wanted to, but ultimately we just wanted to know how many of those little buggers do we start with. Questions on that? Hmm?
So if we're going to find out like how many flies or living things, it has to be a whole number?
Yes.
Okay.
Yeah. Generally speaking, we don't count legs.
Darn.
Darn. Yeah. Now, if we were looking for an average,
Okay.
we would have a piece of a part. If we were looking for an average. If we want to know how many flies we started with, that we would round to the nearest whole number. Okay, let's do a business application. 4 months after it stopped advertising, a manufacturing company notices that its sales have dropped from 100,000 units per month to 80,000 units per month. If the sales follow an exponential pattern of decline, what will be happening after another 2 months? Other than the fact the board of directors is probably going to fire whoever's in charge. Okay, so what are we going to start with here for an equation? If it follows an exponential, we're going to be back to that same equation. This is exactly right. This time t is in months, so just kind of file that away in the back of your mind. What information do we have? T is equal to, do we know the beginning? Okay. And C would be, or excuse me, Y would be 100,000. So we are going to know that 100,000 will equal C e to the K, which means C is 100,000. So we now know that we have Y is equal to 100,000, e to the KT. And what other piece of information do we have?
T equals 2, y equals 80,000.
Read it one more time.
Equals 4.
T equals 4, y will equal 80,000, because after 4 months it dropped, okay? So we know that 80,000 is equal to 100,000, e to the 4k, and we can solve for k. Dividing by 100,000, we're going to get 0.8 equals e to the 4k. So the ln of 0.8 equals 4k, and k would be 1/4 ln of 0.8. So we now have the equation, y is equal to 100,000, e to the 1/4 ln of 0.8t. What do we want to know? We want to know what? When t is 6, because another 2 months, 4 months have already passed, right? And another 2 months t will be 6, so y would be 100,000 times e to the 1/4 ln of 0.8 times 6, and that's approximately 71,554 units. Questions on that?
Where did you get the 4 from for the T?
Up here?
Yeah. Oh,
Sometimes we get tricked when we see a number that's not looking like a number.
Could you move down?
Questions on that? Yes?
Can we see the answer again?
My, off the screen, sorry. Any other questions there? Okay. See if I have any other examples I wanted to go through on that. I think that's good. I think that's good. We've got that. Okay. Other worksheets that I gave you today. Is that all you had today?
Orthodontic.
The brown one, that's right. I knew there was something else. By the way, 6162 homework. Today's Tuesday? Thursday. 6162, have that ready Thursday. We'll have a homework check on Thursday. Tomorrow we're going to do a little bit more 6.2. 6.3 will be on Thursday. We'll get all of 6.3 done in one day. Then next week we'll do 6.4 on Tuesday. Test will be next week, Friday. It's only one day. Well, yeah, you might smile, but that's not a good thing. Because that means
No calculator.
it's, well, no, there'll be a scientific calculator, because you're going to have some crazy number crunching. Well, you can look at these numbers and know that multiplying by hand is a little tedious. However, because it's only one day, that means there are fewer problems, which means you lose more points for every problem. So it's a mixed bag. But there are only so many things I can ask on this stuff, so it's just going to be a one-day test. Questions on where we're going for the next couple of days? Okay, then, that brown sheet, I would like you to take that out now, and you partners have at it, see what you can do with it, and ask some questions before you leave, if you have any. But pretty much we're running out of time. Let's see what we have here.
No, he wants to sit and watch us like for another
Yes, Thursday, you mean?
10 minutes.